for the SAM project. They regenerate what you've done.
Yeah. Okay, anyway, let's move on. So, remember,
So it's all
Reminder.
different now.
Really?
Yeah. No one can cheat.
On those SAM things?
Yeah, everything's different.
I found something on it.
No,
Word
like-
for word on everything.
so, that's three.
No, I'm saying like the ones that people did before. It's not.
Third test next week, review will be posted later. It's everything up to what we just finished, related rates. Everything up to related rates, but after test one. So pretty much that covers everything we did with derivatives, all the way up to related rates.
So it's kind of a little bit of test 2 in there too.
So, what?
Like there's a little bit of test 2 in there.
Yeah, a little bit towards the end of test 2, like the kind of stuff that was on the bonus in test 2, as well as what we've been doing in class since then. And it'll end at related rates, which is what we just finished. Then next week. Supposed to review later today, so you can get started on that. But for now, we're actually going to go into a different section altogether. It's like not calculus, we're going to do something else.
Matrices?
Matrices.
That's
So we're going
complicated.
into section A1. So it's completely different mindset, so hopefully that break gave you a little bit of a palate cleanser. So we're gonna start with some very basic definitions, get you used to what matrices are, how we want to write them down, how we want to do math with them, that sort of thing. And then I'll show you how to enter them into your calculator. I think there's another way to do it other than what I mentioned here. I'll play around with that in a minute. But yeah, we're going to do the basic operations of matrices. So we're going to introduce what matrices are and how we're going to be doing them. And really, the hardest thing here is just arithmetic in this section. It's just that, yeah, it's just a matter of arithmetic. But usually, no one gets confused by these questions or don't understand the concept, so it should be nicer. So we're going to start with section A1, matrices and basic operations. Now, this isn't the best definition of what a matrix is, but it's good enough for us. A matrix is a rectangular array of numbers. So the notation would be something like this, like 1, 2, 3, 4, right like that.
Oh, that's my combo.
Or you write 1, 2, 3, 4, like that. 1, 0, minus 1, 2, 7. That's a matrix. All of those. Now you can use one thing here. We're not going to talk about what this is, but you should just know that there's something exists that has a special notation. So you can use like big parentheses, or you can use brackets for matrices, but do not use straight lines. Like bar. Alright, so this thing, like if I do bar 1, 2, 3, 4, that means something very specific. It's actually talking about the determinant of the matrix and not the matrix itself. So if you want to write a matrix, you either write like big parentheses around a rectangular array of numbers, or you put brackets around a rectangular array of numbers. Do not put straight lines. They mean something else. And let's just look at the anatomy of a matrix. And so let's say I have this matrix 1, 0, minus 1, 2, 4, 7, 1, minus 1, 1. So I defined all these terms that I'm going to use more technically in the handout, but it's okay for me to just show you on the picture how these things will happen. Any horizontal sequence of numbers, we call that a row in the matrix. And these guys are numbered from 1 onwards, starting at the top. In other words, this sequence of numbers, well, that's row 1. And this sequence of numbers, well, that's row 2. And this sequence of numbers, well, that's row 3. Okay? So we call these the rows of the matrix. We number them from 1 going down. Row 1, row 2, row 3. Okay? And we can talk about what's called the columns of the matrix. This is just a vertical sequence of numbers. This is called a column. And these are numbered from 1 onwards, starting far left. So you can have column 1 would just be 1, 2, 1. This is column 1. And column 2 would be 0, 4, minus 1. That's column 2. And column 3 would be minus 1, 7, 1. This is column 3. Okay. So rows is a rectangular array of numbers. We can talk about the anatomy of such a thing. We can talk about a row of things. These are just numbers in a horizontal line, or a column of things. These are in a vertical line, and we number them 1 onwards starting from the top, and 1 onwards starting from the left. Now the specific numbers in the matrix are called entries, or components of the matrix. We can now talk about notation for all these things. So just like how we can have a function and we can give it a name, we can say f of x. Okay, we're talking about the function f of x. And you know there's a formula for it, but you don't want to write down the formula all the time. In the same way you can name matrices. Let's talk about notation. We can name matrices. And this happens usually with uppercase letters. Not always, but that's the usual convention, uppercase letters. So, for example, we can say, let's call the matrix A, that is 1, 2, 3, 4. So now every time I write down uppercase A, you know I'm talking about that matrix 1, 2, 3, 4. We can emphasize the size of the matrix. And now the size of a matrix, that's something that you should have to know. It's basically someone telling you how big the matrix is, and they basically tell you the size or dimensions. That's another phrase for this, aka dimensions. Dimensions of the matrix. That's by someone is telling you how large it is in terms of rows and columns. They say, okay, this matrix is 2 rows, 2 columns. This one is 3 rows, 3 columns, right? So they always label it by rows and columns, and so you can emphasize it by writing this. A is an M by N matrix. So M is always going to be the number of rows. And N, the second letter, is always the number of columns. So they can write the name, and if they don't tell you the definition, they can just emphasize how big it is by using a little subscript. So that's one thing you can know. So that's just some notation there. Another thing, once you make this designation, so that means a matrix with m rows and n columns is called an m by n matrix. Right? And it's read m by n. That's how you say it. Okay, so I can say, okay, there's a 2 by 3 matrix. That means I'm talking about a rectangular array of numbers with 2 rows and 3 columns. Entries can also be labeled. Usually by the lowercase letter. Of its matrix. With subscripts stating the row and column of its position. So, for example, if you call a matrix uppercase A, you might refer to a specific number in that matrix as little a, and then you'd write something like I and J, where I represents the row position and J represents the column position. So let's put this all together with a larger example. So let's say I wrote this example. So I can say A here, it is 1, 0, 1, 1, minus 1, 2. So what we can say A is a 2 by 3 matrix. Furthermore, I can talk about A11, A12, A13, A21, A22, A23. These are referring to specific positions for the numbers in the matrix. This says this is the number in the first row, first column. Let's make these all different so there's no ambiguity here. This is a 3 and a 5. So if you write little a subscript 1, 1, that's saying the number in the position 1, the first row and first column, that's row 1 and column 1, that's this number here, 1.
Wait, what?
A12 means the number in the first row, second column, that's the first row, this is the second column, it's going to be 0.
That's don't like.
What?
I thought I had to solve everything.
What is A23?
So it's row 2, column 3, row 2, column 3 is 2.
Okay, so you do get it. Okay, I'm too confused. Okay, what's 1, 3? What's 3?
3.
What's 2, 1?
Row 2,
5.
This. The other.
Negative 1.
Right?
No, because I thought we had to plug in like 20. Well, before I didn't know how to do it. I would've
Well, I literally just told you how to do it. The first number is the row, second number is the column.
No, like.
So when you say A21, it means second row, first column.
No, when I took the exemption exam, they
Okay.
had the matrices. I didn't know how to do that.
Okay. Well, forget about that. I'm telling you everything you need to know here. Okay. So that's what that means. Okay.
Second row.
Yeah.
So we can talk about the size of a matrix, we can talk about the entries and their locations in that way. So those are some basic definitions. Let's see where I did tell you about that. I told you about rows and columns. I told you about that. I told you about dimensions. Yeah. And I also have some examples there. I did a bit on high position. Told you about that. So let us talk about. There's a very important kind of matrix, it's called a square matrix. There are some things that are only true for square matrices, they're a very important kind of matrix. And it's kind of what you think it would be. A square matrix is a matrix that has the same number of rows and columns. i.e. an n by n matrix. Right? There are some things that can only possibly be true for matrices that have the same rows and columns. And so there are times when I'll give you a rule and I'll specifically state this rule works for n by n matrices. That means it only will work if the matrix is squared. It will not work otherwise. There are many things with matrices that only work on square matrices. We'll see some of them now, but you'll see more stuff like that in the next class. So that's what we call a square matrix. So for example, if I look at the matrix A1, or I look at the matrix B, 1, 2, minus 1, 3. Or I look at the matrix D, 1, 7, 3, 1, 1, 0, 2, 9, minus 1, 7, 4, 3, 2, 0, 7. These are all square matrices, right? They have the same number of rows and columns. This one is a 1 by 1, this one is a 2 by 2, this one is a 4 by 4. So these are all squared. Anything that does not have the same rows and columns, they're not squared. For example, C equals 1, 2, 3, 0, 1, minus 1, or D equals 7, 8, 9, or F equals 2, 0, 4, these matrices are not square. Tell me the sizes. What are the dimensions of this one?
2 by 3.
2 by 3.
1 by 1.
Oh, wait,
1 by
3 by 1.
3 by 1.
Oh yeah, just 1.
1. No, 1 by 4.
1 by 4.
3 by 2.
3 by 2. Number of rows, number of columns, that tells you the size. So we just have these rectangular arrays of numbers. We call rows and columns by horizontal or vertical sequences. The size is the number of rows times the number of columns. And square matrices is when the number of rows and columns are the same. Let's talk about equality of matrices. Equality of matrices. Okay, when would you know that two matrices are equal? Two matrices are equal. They have the same size and corresponding entries are the same. So, for example, 1, 2, 3, 4. 4 is equal to, as you might have guessed, 1, 2, 3, 4. And if we said something like the following, if somehow your matrices, you don't know all the entries, like if I told you 1, 2, 3, 4 is equal to the matrix 1, x minus 3, y plus 1, and 4, you would be able to say that x must be equal to and y must be equal to what? X must be 5 and y must be? Well, if I plug in y equals 3, what would happen? I would get 4 here. Is 4 in the corresponding position? So that can't be y. What must y be?
2.
Must be 2.
Wait, so x.
Corresponding entries must be equal. Matrices are equal if they have the same numbers showing up in the same positions. They're not equal otherwise. So there are times when, so for example, there's a very big difference between saying this and saying this. You can't just say, oh, they're all zeros. Aren't they just both kind of like a zero kind of thing? No, those are very different objects. Okay? You don't want to think of those as the same. They have to have the same size, and all the corresponding positions must give you the same numbers. In any other case, these matrices are not equal. So we can call matrices equal if they have the same size and all the numbers match up in all the right positions. That's the equality of matrices. Okay, so that's what matrices are. That's how we can name certain elements of them, and that's what it means for two matrices to be equal. Now let's talk about mathematical operations on matrices. So we're not just playing around with numbers, we actually want to do math with them, and this will have a lot of applications, operations on matrices, or matrix operations. Matrices is just a plural of matrix. So the word matrices is just a plural of matrix. So now it turns out we can do some arithmetic operations on matrices, like we can add two matrices together, we can subtract them, and so let's talk about the first operation, addition and subtraction, right, which is the opposite of addition. But subtraction you can define in terms of something else I'm going to define. So one basic, very important operation on matrices is you can add them. One important thing, you can add or subtract matrices of the same size. They have to be the same size. If they're different sizes, you cannot add them. It's kind of like adding unlike terms. Matrices don't play well together with things that are not like them when it comes to addition, at least. With other things, maybe. Well, with other things, definitely. We'll talk about that later. So you can add or subtract matrices of the same size by adding or subtracting their corresponding components. So you add or subtract the thing in the same position in two matrices. So let me define something else first, and then I will we'll do some examples. There's another kind of operation called a scalar multiplication. A scalar is just a constant. Basically, you can multiply a matrix by a scalar. you can multiply a matrix A by a scalar, which is a number, K, to obtain, and you'd actually write it down this way, Ka, and this is just multiplying all entries in A by K. So these are very natural operations. They kind of will work out how you think they should work out. That's not always true though. So that's going to be something that comes to matrices. There are a lot of times I'm going to be writing down definitions to you, and it's kind of going to be like, yeah, obviously, nothing is obvious. Do not take that point of view with matrices, right? If I define something and it just happens to be obvious to you, take it as a blessing and move on. There will be things that are not going to be obvious, right? So I have to specifically tell you how to do very basic things. You just need to take those as law and move with it. Don't just think that matrices are going to work how you feel like they should work. This is not true in a lot of cases. So if I write down something and feel obvious, do not roll your eyes, write it down and remember it. We're at the very beginning. A lot of things will seem obvious, but the deeper you get in matrices, a lot of not obvious things start to happen. And we'll get to some of those as well. So let's do some examples here of using these mathematical operations. Okay, so here are some matrices. A is equal to 1, 2, 3, 4. B is equal to 2, 0, 1, minus 3, 1, 4. C is equal to 7, 1, minus 1, 0, 1, 2. And D is equal to 0, minus 1, 2. Now here is goal. I want you to find these guys. Find A plus D. A plus B. D minus A. B minus 2. 2 times A. 2D minus 3A. 1/2D. And if X plus D equals A, I want you to find X. So let's actually do that. A. Let's find A plus B, okay? So this means I want to take 1, 2, 3, 4, and I want to add it to 0, minus 1, 2, 2. And this is equal to. Okay, so what do you think this is?
So 1 plus 0
1 plus 0, you're going to add the corresponding components,
is 1.
and then
2 plus negative
2 plus minus 1, then
3 plus 2,
3 plus 2,
4 plus 2.
4 plus 2. And yeah, that's it. Now you simplify. That's it. Good job. Congratulations. That's the correct answer. You simply add things that are in the same position. This is what I'm talking about. Matrix is going to be doing a lot of arithmetic. And again, it is easy, and it's going to be easy here, the problem is when they get so big that when you're adding and subtracting a lot of things all at once, that's where people mess up. It's not because it's like confusing or it's hard.
Is that gonna
It's just
be-
that you'll make little mistakes, so you have to just be very careful, right? You're gonna be adding a bunch of things or subtracting a bunch
That
of
would
things
be
or
on the
multiplying a bunch
final,
of
like
things,
wrong.
like everywhere, yeah. So that would be A plus B. Okay, and B, correct continuer there. What is A plus B? So this is me saying 1, 2, 3, 4 plus 2, 0, 1 minus 3, 1, 4.
We can't add because it's not the same scale.
Right. Undefined. Good. Okay, so the definition says you can only add matrices of the same size. Whenever they are the same size, you add them by adding corresponding components. If they're not the same size, they cannot be added. It's undefined. Okay. Let us move on to D minus A. So this is me taking the matrix 0, minus 1, 2, 2, and I'm subtracting the matrix 1, 2, 3, 4. Okay, so what is this going to be?
So it'll be 0 minus 1, negative 1 minus 2, 2 minus 3, 2 minus 4.
Right, subtract corresponding components.
So it'll be negative 1,
You get that?
negative 3, negative 1, negative 2.
Yes. So, in general, you can skip this step, you don't have to write it. You can just jump to here. However, if you know you're someone who you kind of suck at little arithmetic calculations, just write out every step. It'll take you a few seconds longer, but it's better you just don't make a mistake on something very simple. So you don't necessarily have to write out this line. You can do it in your head. Oh, it's 0 minus 1, it's minus 1. Minus 1 minus 2, that's minus 3. 2 minus 3, that's minus 1. 2 minus 4, that's minus 2. You can do that in your head and that's fine. But if you need to write out steps to keep things straight, by all means do it. It's not worth getting something wrong. That should really be simple. But yeah, to subtract them, you subtract the corresponding components. Forgot something a little harder here, B minus C. So this means I want to take a matrix 2, 0, 1, minus 3, 1, 4. I want to subtract the matrix 7, 1, minus 1, 0, 1, 2. So what is that going to be?
Negative 5.
Minus 5.
Negative 1, 1, 3, 0, 2.
3,
Wait, it's negative 3.
then
0, 2.
okay. That's wrong.
But isn't the first one 0?
It's
5,
zero.
negative 5 minus 1, 0.
Huh?
The first one.
Okay. What's 1 minus minus 1?
Oh,
It's 2.
that's 2.
Oh,
Okay. Now you guys are seeing where the mistakes come. It's not hard, but when you're adding up a bunch of numbers, trust me, you're going to make errors, right? And this will happen a lot, especially in the beginning. You just messed up adding 1 to subtracting minus 1 from 1. That's where the mistakes creep in. When you're starting doing a lot of them all at once, you have to be very careful, right? It takes some practice for you to really be able to jump to it, so be very careful. So normally when you make a mistake in a matrix problem, it's going to be a stupid mistake like that. You're going to kick yourself in the head for making it. So be very careful, right? It's just basic arithmetic, but when you're doing a lot of arithmetic all at once, it's easy to have a slip up here and there. So you really want to be very disciplined how you're doing this. And if you're practicing a bunch of things and you notice that you make slip ups like this all the time, then I would recommend you just throw in those extra steps. Just literally write it out, what you're doing. Write out this step. Right? So ordinarily, this will be fine, but if you realize that you're just stuck at adding matrices, you always mess up somewhere. Take time, write out the intermediate steps, and then move on. That was B minus C. Okay. What is 2A?
Is that 2468?
That's 2 times 1, 2, 3, 4. This is what is called a scalar multiplication. So I'm taking a matrix, I'm multiplying it by a number, and this pretty much follows the distributive law. The rule for this is you take that number and you multiply each entry in the matrix. So it's going to be 2 times 1, 2 times 2, 2 times 3, 2 times 4. That's what's going to happen. Now, ordinarily, you can skip this step, but like I said, if you realize you're prone to making a lot of errors when doing your arithmetic, I'd write that out. So this would be 2, 4, 6, 8. So that's 2 times 8. This is called a scalar multiplication. F. Or if I wanted to do 2D minus 3A, that means 2 times 0 minus 1, 2, 2, minus 3 times 1, 2, 4. You're telling me the answer?
Sorry.
9 is 3?
-8. -5 and
Okay. Let's do the intermediate step to check this. So this means you're going to take 2, you're going to multiply everybody here. That's 0, minus 2, 4, 4. You can take the 3, multiply everybody here. It's going to be 3, 6, 9, 12. Now you're going to subtract these. 0 minus 3 is minus 3. Minus 2 minus 6 is minus 8. 4 minus 9 is minus 5. 4 minus 12 is minus 8. So that's the answer.
Oh my God, crazy.
That's crazy, right? It's kind of suspicious. It's supposed to be that easy. I mean, a few seconds ago we were doing implicit differentiation and my brain was dying, and now it's like, I don't know, I don't trust Jhevon. I feel like he's gonna. Like in like 5 minutes he's gonna like do something. I know it. I just like I'm waiting
Is this
for
on the test?
No, not test two.
test 3? No. Test 3 next week ends at related rates that we did before. The last test, test 4, is only on matrix stuff. So this will be on test 4.
What about the bonus?
Hmm?
What about the bonus?
I'll put this on the bonus for test 3, but it's not in the actual test. So half D, what does that mean?
So you're multiplying half by 0, negative 1, 2, 2.
0, negative 1.
Wow, this is
Okay. H.
This is right.
Okay, so
This is
okay,
where
do you think you guys can do algebra with these things? How would you solve this? So if someone want to find x, it's like, yes, I knew it.
So
You
subtract
first
D.
You just
since D equals to that,
No, over.
you would subtract D onto both
Yeah,
sides.
so
Yeah, you
A
can
minus-
actually do that. So you can subtract D from both sides.
And then you do A minus D with the matrix,
So this is
since
1,
it's
2,
the same.
3, 4, minus 0, minus 1, 2, 2. And then that would be 1 minus 0, 2 minus a minus 1, 3 minus 2, and 4 minus 2. So that would be your x.
So why do they
So
make
this can be, this is one of those things that are obvious, but really what you should realize is what's happening here is that you're taking x plus the 0, minus 1, 2, 2, equals A, 1, 2, 3, 4, right? And what you did is, you can subtract D from both sides by doing the following. You subtract this guy. And on that side, you subtract this guy.
That's my work.
And here, you'll realize that all the things kill each other, you get just 0, 0, 0 plus x. But it turns out if you're adding this to x, you're just adding zeros to everyone, so that just
So
becomes
it's just
x
x.
itself. Right, so that's really what's happening here. But yeah, for addition, you can just move things across the equal sign pretty easily.
So why do they use matrices? Like, what is that for?
Oh, they're used all over the place. If a math person is thinking of a matrix, they actually think of them as functions, not as like numbers. So this is like a function from a two-dimensional space to a two-dimensional space. It's like a higher dimensional way of writing the equation of a line, basically. So, but you don't really have to worry about that. So the addition part, this seems pretty okay. This seems obvious. Now, if you're in this situation, and I ask you to solve for x, what would you do?
Divide.
Yeah, so now we're no good. Yeah. There is no such thing as division when it comes to matrices. So addition and subtraction is obvious, but not everything is obvious. This is one thing I'm warning you guys about. Matrix multiplication is actually not an obvious thing at all, and it turns out the way that we're going to define it, there's going to be no reverse in general. There's no reverse
So
of
it'll be
multiplication.
undefined?
It depends. And we'll talk about when it would depend. Yeah, but you can't divide by a matrix, right? That's why we define addition and subtraction first. So that's the easy thing, that's where we start with. When we talk about multiplication, you're gonna realize it's gonna be kind of weird why it's defined that way. And then you're gonna realize, well, we can't really reverse this, so how are we gonna divide? Well, you can't in general. So multiplication is weird with matrices. Division doesn't exist at all. Like, you can't actually do it. You can't
Watch that
divide
on
an
the
equation
test.
by a matrix. It doesn't make any sense. Let's talk about a few other definitions, and then I'll show you how to enter matrices in your calculator. Maybe you can even redo some of these guys. Let's see here. Okay, just some more definitions here. There's called what we call the zero matrix. And this one is what you would think, at least at this level, matrix where all entries are zero. I want you to notice they can be different sizes. You can have a 1 by 1 zero matrix, you can have a 2 by 2 zero matrix, you can have a 2 by 3 zero matrix. But if you have everyone being zero, it's called a zero matrix. They can be of different sizes, but they are very distinct from one another. This is not the same as that, right? None of these zero matrices are the same. They're zeros in their little world, right? In the land of 2 by 2 matrices, this guy is the zero. In the land of 2 by 3 matrices, this guy is the zero. And these different worlds don't always play well together. Like, you can't add people from these two. So that's a zero matrix. Another important definition is what's called the main diagonal of a matrix. If a matrix is square. So this is a definition that only applies to square matrices. Sometimes they'll just call it the diagonal, but they really mean the main diagonal. Is the entries running from top left to bottom right. That's the main diagonal. Okay, so I can do an example here. Example, let's say my matrix A is 1, 0, 1. 2 minus 1, 7, 0, 0, 3. then I call the main diagonal would be this sequence of numbers here. It runs from the top left to bottom right. That's the diagonal. It's a diagonal of a matrix. Or the main diagonal. So a matrix, a zero matrix is just a matrix where all entries are 0. And the main diagonal of a matrix is this list of numbers running from top left to bottom right. Here's another definition. A very important kind of square matrix is called the identity matrix. We'll learn why it's called the identity matrix in the next section. The name isn't obvious here, but this, I probably have to talk about a diagonal matrix first. A diagonal matrix. Matrix where all non-diagonal elements are 0. So that's a diagonal matrix because the guys are on the main diagonal, but everywhere else is 0. Or 1, 0, 7, 0, 3, 0. 0, 3, 0, 0, 0, minus 1. That's a diagonal matrix. You can have 1, 0, 0, 0, 0, 0, 0, 2. That's a diagonal matrix. You'll notice that if you look at the numbers on the main diagonal, look at everyone else. Everyone else is 0. Whenever everyone else is 0, except maybe the guys on the main diagonal, these are called diagonal matrices. A zero matrix is also a diagonal matrix because you don't care about what's on the diagonal. You care what's not on the diagonal. Everyone that's not on the diagonal is a 0. It's a diagonal matrix. There's a very important diagonal matrix. So these are just the names that we call them. It's not really something you have to figure out mathematically. So there's something called the identity matrix. Like I said, you'll see why we call it that. This is a diagonal matrix. Diagonal matrix. Right? So it means it has this property where all diagonal elements entries are 1. So whenever you have all 1s on the main diagonal and 0s everywhere else, this is called an identity matrix. It's a very important kind of matrix. So for example, you can have 1, that's an identity matrix. 1, 0, 0, 1 is another one. 1, 0, 0, 0, 1, 0, 0, 0, 1, that's another one. And of course, you can keep building up. These guys are the identity matrix. Notice that they are diagonal, therefore they're square, and we actually have a very common notation here. So the n by n identity matrix is called I subscript n. It may be written as I if the size is understood. But if you want to emphasize the size, you should write I with a little number. That means this guy, I can call it I1. This guy is I2. This guy is I3. And this guy is I4. So this is a 1 by 1 identity, so it's I1. A 2 by 2 identity is I2. A 3 by 3 identity is I3. 4 by 4 identity is I4, and so on and so forth. An n by n identity matrix is IN, and it might be written as I. Now, this is a designated letter, meaning if you're looking at a matrix problem and the letter I shows up, it always refers to this matrix. It will never refer to anything else. Okay. The identity is uppercase I is a reserved letter. No one calls I anything else, they'll never call it I. Okay? Once you see I in a matrix problem, it's referring to this guy. Right? He's important. He gets his own designated letter. Right? He's that important. It's a very important matrix. It's called the identity matrix. And we might denote it I in a problem. Okay, let's talk about transpose, and then I'll show you the calculator. Let A, let's say M by N be a matrix. Right? So this is a matrix with M rows and N columns. The transpose of A aka, I might call it just A transpose, is the N by M matrix that basically switch the rows and columns, switches the rows and columns of A. It is denoted by A raised to the T, uppercase T. Okay? So this literally means you take the first row, turn it into the first column. Take the second row, turn it into the second column. Third row, turn it into the third column, and so forth. Switch rows and columns. Corresponding rows turn to their columns. So let's actually just find the transpose of all the guys in the example we just did, the A, B, C, D. We're going to find all their transposes. A was 1, 2, 3, 4. B was 2, 0, 1, minus 3, 1, 4. C was 7, 1, minus 1, 0, 1, 2. And D was 0, minus 1, 2, 2. Find the transposes here. This would mean that if I take A transpose, what do you think I would get? What would the first row be? 1, 3, 2, 4. Right? Notice that I took the first row, it became the first column. And the second row became the second column. So it switches the rows and columns. That's all it does. First row becomes first column, second row becomes second column, etc., etc. You keep going. What would B transpose look like? First of all, tell me what is its size. What size should this be?
2 by 3.
B transpose.
3 by 3.
3 by 2. Because B is a 2 by 3, the transpose is just going to switch everything. So this will just switch the order, 3 by 2. And what specifically is it going to be? So notice the 3 rows, 2 columns. Tell me the first column.
2, 0.
2, 0, 1. And then minus 3, 1, 4. Similarly, I can talk about C transpose. First row, turn it into the first column. Second row, turn it into the second column. I can talk about D transpose. 0, 1, 2, 2. Called transpose. Switch the rows and columns. Right? And it's always uppercase capital T. Right? And that's always what this would mean. It means this transpose. about the calculators? Get out your calculator. You always have matrices in both sections, so you should know how to use your calculator with matrices, as well as being able to do them by hand on things like this. Jesus.
Are there usually a lot of matrices on the final?
Yeah, there are usually a bunch. There are a few.
Right.
5, 6 problems, maybe? Yeah. So the file has like 35. 5, 6, 7 roughly would be on matrices. You'll have a couple in there. You'll have a few around, strapping around. I don't know of a standard number. Usually when it comes to like related rates, you have like one. But when it comes to matrices, they're fairly common. It's a decent chunk. So how do we actually do matrices in a calculator? So first thing, of course, is to turn the calculator on. Okay, so now we have a syntax. We write the matrices in square brackets. Okay. Now, how you do it is you literally write the rows one after the other, right? This is described in the handout, but I'm only doing it by talking now. So you're going to type out the first row, then type out the second row, then type out the third row. Now, it's important how you type these out. In a row, you separate the entries by commas. Once you want to switch to the next row, you put a semicolon, okay? So, for example, I can go here, where's the square bracket? It's right there. We open that, and then I'm going to say, let's say I want to do the matrix A from the previous example, 1, 2, 3, 4. So the first row is 1 and 2 in the first row. So I'm going to type 1, comma, 2. Okay, so that's the first row. Then I'm going to want to put the semicolon. First semicolon. Do I remember where the semicolon is? Come again?
It's right underneath the comma.
It's right underneath the comma. See second function for the comma?
Yeah.
There's a semicolon. It doesn't really show up on this screen, but on your calculator you'll see it.
Parentheses or what? Brackets?
So
No, the semicolon.
No, like in the.
it's on the 9. It's actually on the 9.
To start off, it's a bracket.
So you start off with a bracket, which is above the comma. Then semicolon is below the comma, which means second function, you press 9. Okay? So then I'm going to go second function, press the 9, that puts in the semicolon. Now I'm going to type the second row, 3, comma, 4. And I'm going to close the parentheses. So second function, this. Okay? Now if you press enter, you'll see it look like a matrix. 1, 2, 3, 4. Right? So that's the first one. Right? So you type the rows and then the one row at a time. I believe that this way is fine. I thought there was another way though, but now I actually don't remember how that would do. Let me just try something here.
You see, there's actually a lot of matrices.
Yeah, there are a bunch, right? Like
Yeah,
how many
like-
did you see on one of the samples?
1, 2, 3, 4, like 6, 7.
Yeah, so it's usually around there, 5, 6, 7, maybe 8.
Like it.
Yeah, so you have a couple notations, learn one of them, always do that one, right? This is another way you can write down a matrix. You just put a square bracket, and within each bracket, you actually type,
Wait.
you type the rows. This way, however, it's actually, it's more in line with how you would type it on Wolfram Alpha, for example. So maybe I should show you guys that as well. If you wanted to go and check your work on Wolfram Alpha, can also type out the I think it works with square
It's
brackets. I
actually
usually
a-
use squiggly brackets, but it works with square brackets as well.
It's actually the same problem on the final for the song, but it says find a of -1 to the power of -1.
That means something else. We didn't talk about that. That's inverses.
Yeah.
So if you're doing it here, you can type 1, 2, 3, 4. That's not it. I normally use squiggly brackets and that works. 1, 2. 1, 2, 3, 4. Okay, and that's the matrix 1, 2, 3, 4. So it should work with regular brackets though. Let me check. 1, 2, 3, 4. Yeah, so you can also think of it that way. Right? So you can use either notation, but if you want to do something in Wolfram Alpha, you can also do that here. However, let's put in one of the other ones. Let's put in. Okay, so now once you actually type a matrix, right? You can actually, to make it easy on yourself, you can store it in a letter, right? You can use that by the storing key right here. So let me show you how to create this matrix and call it A. Okay, so we can go here. We can go, all right. So you want to create the matrix bracket 1, 2, second function semicolon 3, 4, second function close bracket, and then I can press the store key right afterwards. Store this in the letter A, go alpha A, enter. And so now it says, okay, I created the matrix 1, 2, 3, 4, and I put it in A. Okay, now let's actually create our matrix D in the same way. So if I want to make D, bracket, D is 0, -1, 0, -1, you'd use this minus. Second function, semicolon, then the last row is 2, 2, 2, 2, close brackets. And what I can do is I can store that in alpha D, enter. So I've created two matrices, A and D. A is 1, 2, 3, 4, D is 0, -1, 2, 2. Now let's add them. So what you can now do is you can now do operations with these letters. So you can say, let's take A and add it to D. It can add it for you. You can subtract it. You can do all the other things that we spoke about. You can even do 2 times A. And it'll give you the 2, 4, 6, 8. Let's create B and try to add those. Let's see if we can confuse the calculator. So B would be 2, 0, 1, 2, 0, 1, semicolon, -3, 1, 4, close parentheses. Let's store that in the letter B. Okay, so that's B. Now let's try to take A plus B. Okay, see, now the calculator tells you that cannot be done. There's a dimension mismatch. So your calculator knows you can't add things. So that's not going to work. Let's see if I can trick it and divide something.
How do you put that arrow in the dimension?
Huh?
Like
This here,
It's stored.
it's stored here.
Oh,
It's a store button. So it says, we take this and we put it inside this variable. So every time you type B, it means that matrix. I never actually tried if we can confuse it, but let me try now. Okay, what if I took A divided by D? Yeah.
No
it
division.
knows you can't divide it. It can multiply. So escape. So I could actually take A times D, and that actually does make sense. I would actually get 4, 3, 8, 5. Now you might notice those numbers are not really obvious, but we'll actually talk about that later. Matrix multiplication isn't that obvious.
Wait, you times it by D. I thought it was D.
Huh? No, I times it by D.
Can't it times by B too?
What? A times B?
Yeah. A bit different.
You could, yes.
There's this question that's matrix.
So here's something interesting. Look at this. Take A times B. Okay, you actually get an answer, right? Now look at this. What is B times
A.
A? What do you think that's going to be?
It's gonna work.
It's not going to work.
So go for the bigger number?
Okay? So again, when it comes to matrices, not everything is obvious. So when I write down a rule, and of course, Jhevon, what else would it be? It's not always obvious. A times B is not always the same as B times A. There are a lot of rules that you'd expect to work out that they're not going to work out. So you have to be very careful with matrices. I mean, again, it's not hard, but you have to make sure you know the rules and just don't make silly mistakes when
There is this
adding.
question on the final that I thought it's not, like, cannot be multiplied, but it's actually.
Anyway, we'll take a break and we'll come back. So I actually want to talk a little bit more about matrices for the recitation session. I'm trying to free up some time for the mock final at the end. So you can take another 10-minute break and then we'll probably talk about multiplication, like what actually happens here.
Can you show me how to do this one?
Well, after
This
the
is
break.
matrix product. Can we do that?
After the break, why are you